Okay, so welcome to the live tutorial of LTC, l2race lite done by our excellent Florian.
Okay, Michael, is it true? Or
yeah.
have you already installed or set up the master branch from the
yes
common road MPC?
Yeah, I'm currently on the master branch, and I have managed to run the run simulation script. Which is currently just doing a constant control or something and drive straight off the track immediately.
Yes. Okay. Perfect.
Yeah.
Yes, I made this. The run simulation script is like the easiest way of implementing a custom controller, and here you can try setting your own control inputs. And as you found out, it's just static at the moment. And so maybe we go first through the racing framework and then through the controller. Is it okay?
Sounds good.
Okay. So first of all, I have this racing folder here, and here is everything I copied from l2race itself from the big project. And as the simulation needs a track, of course, in the car, and I have this track class, so everything that's directly bound to l2race is in the racing folder. The track loads the same track from l2race. I really copied them. You can also see them here. It's like the images and the track info, and this track class basically loads the track info. Okay, here we were. And yes, it sets the waypoints, and you can access all those internal variables for orientation where you are on the track. And also there is a distance to track, get closest waypoint index. Those functions might be useful if you want to implement your own controller. Distance to endpoint, again, yeah, just basic functions. And well, you just stop me if you have questions or if anything is not clear. Is that okay?
Sure.
Perfect. Then next to the racing, there is the car that we need to initialize with the track. And the car has, again, some basic functions and some basic properties where you can just ask for. The car dynamics function now is from the common road library. This is the one from Munich. So I didn't write this code, but it just defines the states of the car, and like described in the paper, it will calculate the car dynamics due to a given input. I'm not sure if it was you that asked, but maybe you have seen in the common road models folder, this document might be useful to understand what's going on. This is basically a description of what this whole library does, but I didn't touch it. We just use it for the state evolution calculations. Okay, so I'm kind of overwhelmed with this Zoom window. Okay, here we are.
Shortly remind me, what is the current state regarding the Cyton? Do we use it or do we not use it?
No, we don't use it. It is fast enough without. At the moment, we don't use it. Okay. Yes, we used to have a Cython implementation for acceleration. It's like a library that converts Python code to C, but we don't have it anymore. It might be still in the documentation, so don't get confused. The car can do a step. And the step, basically, I try to comment these functions. We take a control input and the state that the car itself already has, and it will just the next state of the car. And I have programmed some extras. For example, the car notices if it went around the lap or not, but this is not important. You will notice it. And it can draw its history, the car. This looks like this, the car history. And as soon as you say car.draw history, you get the trajectory or the trace of the car compared to the racetrack. Yes, and this is just the static control. And the objective would be, the goal would be to like drive around the track. This is quite everything that the car does. It can also save the history, not draw it. Then it will generate the CSV file of all states of the car during the simulation in the folder experiment recordings. So this looks like this, more or less. So this is the drawing and the CSV. And this might be useful for implementing controllers. And you might also want to have the CSV as a training data file if you want to train in a sequential data. Good. This was quite everything about the racing itself. And now I think we can go through the neural MPC controller. And did I understand it right that the idea of the project you do is to retrain it, but with sequential data and a recurrent neural network?
Yeah, that's what I was planning.
Okay, perfect. So the controller has basically two parts. One part is really the MPC itself that solves the model predictive path integral. We go through that first, and then I show you my neural network prediction, which will be probably your main thing of interest. So the run MPC looks the same like the run simulation, but we have here a car controller class instance that that calculates the next car input, and then the car does a step where depending on what the car controller says. And the car controller basically does a model predictive path integral. So, okay, initializing is not so important. It will first, it can simulate the step. This is the same function like the car step, but it won't execute it. It will just give you, as a result, the next state. This might be a bit confusing with the states. I normally use just the indices to calculate with the states. And in this paper, in this PDF, the states are shifted one number. So here, for example, you have x1, x2, x3, x4. But as we start with 0, so x next 4 is actually the fifth state. Maybe you know the problem if you.
Yeah, it's the zero-based indexing platform.
Yes, perfect.
Yeah.
Well, this is a bit confusing maybe, but you get used to it. Based on the step, we can then simulate the trajectory, which basically simulates just multiple steps. And we see here the argument is a control input, which is just two numbers, an array of 2. And here we have control inputs, which is a list of control inputs. So n by 2 array. And this will simulate just a trajectory that the car will do for a certain sequence of control. And we go one thing further. We have now a distribution of control sequences, and we can simulate multiple of those trajectories, which we need to solve to simulate this path integral, like overall states. This will.
And sorry, if you just go back to the previous function.
Yes, sure.
The input there is a trajectory of commands into the future. Okay.
Yes, it's just a list. I try to mention the type.
Yes, sorry.
Really a list of control inputs, and in the README, you also have the terminology of a control input, which is an array, a float array with 2 numbers. So this also is described in this paper. How many, which value means what? So the first one is the steering between -1 and 1. The second one is the acceleration. Yes, and then we do just I closed the file. Hey. Okay, here we are. Yes, and you see for each control input in control inputs, we then just simulate the step. So yes, this is just multiple of this. And again, we take again a multiple. So we don't simulate one trajectory, but the distribution of trajectories. Want to do this multiple times. Looks like this. So one line, like for example, the pink one is one trajectory, and all lines is a distribution of trajectories. And we rate this with a cost function. So for each control input, again, in the distribution, we simulate the trajectory with the list of control inputs, and we rate it. The cost function is implemented in the trajectory. So if we get the trajectory, we also know what it costs.
And the cost function is applied pointwise?
Yes.
Like there's no carryover between.
We will come to that. I can show you the cost function. Anyway, the distribution is this, and here you can see that we can get to the best trajectory, and we choose this, and this is basically how the MPPI approach works. And okay, we have the same function again, but with the neural network. The neural network is more efficient for multiple data inputs, and at the first function we simulate trajectory by trajectory. But if you want the neural network to simulate it, we do it step by step, and we have to swap the axis twice. That's why there is another function. But yes, this shouldn't be too much confusing. And this is another thing. This is how we come to the random control inputs, but we get to that after the cost function. And here is the cost function. And we rate the trajectory. And in the moment, the cost function is really primitive. We just look that we stay more or less in the middle of the track and be as fast as possible. So the distance cost is, I think it's this squared distance to the track. And here we see also that we use the track object. Let me find it. Distance to track is the self.track line is updated in every step, and this is an instance of the track class, and we can get the distance to it, we square it, and we sum it up for every state. So this is the pointwise thing you were asking. Exactly. Then there are some other costs. For example, we don't want to leave the racetrack. We have defined a track width. Yes, this is like 1,000 is the maximum cost, and the weights for a cost of 1,000 will be 0. So 1,000 cost is handled like infinity cost, and this won't be rendered at all. And we don't want to go under a minimum speed, but you can experiment with that. I'm sure it's not at all the optimal cost function, and you might get much progress by engineering the cost function in a better way if you're interested to do this. The angle cost might be a bit confusing. This is just we penalize when we enter a curve too fast. So it looks ahead, and if a curve is arriving, it will. The terminal state 3 is the speed at the end of the trajectory, and we penalize if the speed is high and the sum of angles is also high. So yes.
Sorry, the sum of angles is the angles in the trajectory you're plotting, or along the curve itself, the track itself?
On the track itself.
Okay.
Yes, so we have the absolute. Oh, it's called squared. It should be like absolute, but you see, it used to be squared. The angle is just the angles of the waypoint of the self.track. Yes,
okay.
From the closest one to a certain threshold. So like the next 10. We sum the absolute angles up of the next 10, and if this a large number, we want to be slow because of the angle cost.
Okay.
Exactly. Okay. Good. I think this was the most important. Now what the controller really does is You see it here at every instance, at every moment, it will do a control step. This is the last function here. Control step will first update the track line, as I mentioned. It has to know where it is on the track and which is the closest waypoint and so. And we sample the control inputs. This is the function that I skipped. This just generates a normally distributed set of control sequences from hard to the left to hard to the right and anything in between, which gives this beautiful trajectory distributions. Depending on the, sorry?
I was going to say, why, I'm sure it doesn't make that big a difference, but why a normal distribution versus uniform?
I tried both. I made better results with the normal because the chance that the car goes really hard to the right is not so high.
Right.
So, this is depending on the track. Maybe if you have a more complicated track, you might want to have a normally distributed. But it's just experimentally like guessed. It's not really a reason behind. Okay, depending on the variance, it can look more chaotic, for example, like this. But the more chaotic it is, the better is the optimal trajectory that it finds, because here it actually does first nothing and then it will go through a curve, while here it will do the curve from the beginning. So you can also play with the variances. And I'm also doing at some point history-based trajectories. Here we are. History-based means I do a normal distribution around the last optimal one. So if you see the pink line, this is the optimal one, and in the next step, the car will be here. And we do a normal distribution just around the pink one. And we can do this with a smaller variance, obviously. This looks like this for the next step. Okay, I think this is pretty much the magic of the MPC. And now I think it will make sense to go to the neural networks. The neural networks of the controller are hidden in the simulate step, probably. Simulate step. We have different kinds of predictors. We can predict just the real ground truth car dynamics with the Euler function, or with ODE-int, which is a bit more accurate than Euler. It's just a Python library that integrates functions. And here is the neural network predictor, predict next state. And this is the part where it might get exciting for you. So let's have a look at the neural network predictor. In this, all in the folder NN prediction. So from now on, everything that has something to do with neural networks is here. We first of all have to train the neural network. This all happens in the training folder. And I try to keep it as simple as possible while having as much features as possible, which is kind of a trade-off. But basically, we save some settings for the neural network. We load the training data from the data folder. Training data are just CSV files, and you will change this for the sequential training probably. And oops, I closed the file again. Sorry for that. Data train. So we bring them into a write format where we can train the network. And then I play around a little with the data. For example, I predict the delta, which is like the difference of states instead of the states. So this is the right-hand side of the ODE that I try to predict with network. Like this, we have the state invariance guaranteed. So my training data is all around 0, 0 position, and it doesn't matter the position for everything else. And then we have just the Keras neural network. I assume you're familiar with Keras, are you?
I am, yeah.
Okay, perfect. Yes, so this might be the file to make your changes. We compile it, we save it. What is maybe a bit different is that we save The normalization constants and the scalar and the neural network settings we save just into the models folder. So this is the folder that Keras exports, and we can just have a look. Yes, this one predicts delta. It has this name. It cut invariance, so it doesn't have X and Y as input, number of epochs and so on. We just save this into the model folder. But you're free to do whatever you want. Just maybe it might be easier if you understand my code. Okay, this is the training, and now once the model is trained, we want to test it. Now I have to think. It might be important to show you the SI toolkit. This is how I test my things, my neural networks. And let me quickly activate my Conda. Okay, I think I can show you now. After training, we want to test it, and everything that has to do with testing is in the SI toolkit testing folder. And we have here parameters for testing, and I have the framework set up that we can just put here the name of the neural network itself in the tests thing. So this is like a fusion between Martin's and my ideas, probably. And I want to run, sorry?
I was going to say, so when you put all those three names in there, it's going to test the performance of each of those models.
Yes, okay. Against the ground truth. So I can show you the Brunton test by running the SI toolkit testing. Run Brunton test. And now, so this tests it for all those three, and it really just takes. It will initialize a car controller that I showed you before with this argument as a predictor, and the car controller will predict the states and will return it to the Brunton test. And this is what it looks like. This is Euler, so the ground truth model is of course perfectly accurate on all states. This is one neural network. This is a bit inaccurate, but still pretty fine. If we show all, we do it for every point, and we see like how well it performs around the racetrack. And this is a smaller network. This is a little less accurate, and we can go through all states. So X1, X2, this is still position. X3 is the speed, and we see how it performs. Yes, this is pretty useful because running simulations on the MPC with neural networks that are inaccurate, they just need a huge time to calculate and lead to no results. So I recommend using this if you're so far. And so how this works is it will initialize the controller, as I said, with a certain predictor class. And in the controller, you already saw that simulate step. If the predictor is a neural network, the NN predictor predict next state is the thing where the magic happens, or actually just a prediction, but here we are. No, prediction.py in NN prediction. We just load the model. We normalize the data, and predict next state is really, we just give the state or a variation of the state depending on how we trained it. And the control, we give the state and the control as an input. And the model that is loaded predicts the next step. And it will return just the next state mapped on like 0 to 2 pi for the angular sizes, but that's it already. As I said, it's pretty fast predicting multiple states. So I normally use this function, not the one for single steps, but more like for 1000 trajectories, this will run in 0.1 seconds or so. This is pretty fast.
It's pretty fast.
Yes, it's much faster, by the way, than the ground truth prediction, because the ground truth Euler stepping is implemented in Python, and this is like 100 times slower. So I was really struggling with simulation times before I got the neural networks. Yes, there are some test scripts. Yes, so the important things for you will probably be the training and prediction files. And yes, I invite you to make copies of them and do whatever you like, and ideally on sequential data. Yes. Oh, I forgot to mention the Brunton test. It works on test data. So the curve I showed you, let me run it again. So just two more. Okay, I forgot to mention that this curve is from a test run around the track, and it is located in the experiment recordings dataset test.csv. So this is just like one simulation, and you can do here whatever you want, but I can send you just the CSV files that I use. And I think if they are accurate on this test data, they might also be on the racetrack because it's pretty similar. Exactly.
Okay, looking in that folder right now, I just see a README file.
README.
Yeah.
Here, this one.
Yeah,
This was just for me, for myself, to know where this data comes from. So we see it's from track 2. It's with the ST model. I recommend not changing the model. So of course you can also try with more complicated models, but I don't have experience with it, and I might not be able to help. And sure. If you stick on the same model, I had a huge overhead in time when I tried to change the model and nothing worked, and I had to change it back, and it's like distributed in 5 different files, and so I recommend using the ST. This is also the one that l2race works with mainly.
Okay. But I guess my question was, that data that's in that folder on your computer, should that be committed to the repository, or does that get generated automatically by some other process?
It's not automatically generated. Okay. You can generate it by running my MPC controller. It will generate the data for one lap. I can also show you, but I will also send it to you, so you don't have to deal with things like this. Also, the data generation of the neural networks works in another way, but I will give you the data. So let me maybe Python run MPC, and now we run a simulation around the track, and we can the life history is plotted normally. Okay, it's not. Let's go to the settings. Globals.py is the settings, by the way. Here we have all kinds of variables that I told before you can play around with. If we draw the life history, the car will. I also draw the rollouts. I think this is good to show. If I run MPC now, we can spot the life history that the car does at every time step. So we see it moving inside the plot. If you're using PyCharm, I'm not sure how often a PNG is reloaded. In Visual Studio Code, it's pretty fast, but it might be a matter of settings. And we see that the car completes the track. And once the experiment is done, it will take 1,000 steps. It will be saved to the experiment recordings folder. And then you could technically put it in the dataset test and so, but as I said, I will send them. You see also that it tries to brake in front of the curves. So this is a direct consequence of the cost function. Here it is a steeper curve, so it will brake more. Yes, but just play around. What I also wanted to show is the rollouts. So this is the small variance curve of trajectories that are close to the optimal one. Okay, this is not so beautiful as I thought. Okay, let's draw all. I just have the track width to 20 or so. Then it will draw all of them and not only the ones that's on the track. But this is good to see how the MPPI rollout works. So this is every trajectory that it calculates. And it calculates 250 in every time step. And the neural network is really fast in doing this. The most time is for drawing. So if I do not draw the rollouts, it works real time normally. Like 5 iterations per second is real time. So, okay, it's not, oh, I'm still drawing the history, but 2 seconds, 2 iterations per second. If you don't draw this, it's real time. Good. Maybe let's go through the settings at last. So the control sequence is just 0.2 seconds. I have no idea what happens when you change it. If it is implemented correctly, that it will literally change it everywhere. It should. You could try it with 0.1. If you want to train the network also on 0.1, but for me, it works like this. Yes. Euler step. Okay, this is just for the ground truth modeling, and the simulate. This is just for experiments. Like the simulation length is 1000. What do you want to draw? And current track. Until here, it is important for you. So we can set some car parameters. We can also exit after 1 lap if we want to measure the time. Yes, it should more or less be self-explanatory. We can continue from the last state if it is saved. This is also maybe important. I normally use this to debug different difficult curves. Yes, and track width depends on how good your controller acts. The track width of 4 meters. The car might crash after being further away than 4 meters from the track, but you can put this value to 100 if you have no good controller yet, such that the experiments will run either way. And this is the predictor for the car controller. If I write here Euler, it will predict with the ground truth, and otherwise it's neural network and the neural network name. And for the rollout, we have 1000 trajectories for the beginning with the high variance, this curve. And we have, it's 500 per rollout at the moment, which is this curve. Yes, this is just the MPC settings. Okay. I hope that summed it up well, and did you understand it?
Yeah, no, it's good. I guess one thing I don't have right now is a copy of your dense model.
Yes.
And I was wondering if you could show me the command I need to run to train.
Yes, I tried to.
Or did you show me that already and I just blanked on it?
Sorry again.
I say, or did you show me that already and I just blanked on it?
No, I didn't show that.
I'm sorry. Yeah, if this is in the README, I can just go read the README.
Yes, the README is pretty new. I tried to keep it as good as possible, and you can download the dense models. I have it on Dropbox. I have this link. You can download them directly, and you might have to generate this models folder in the NN prediction models. This won't exist. I tried to keep it, but it somehow doesn't work. Anyway, just put it in there and it should work more or less without any other changes. Yes. Okay.
But sorry, if I wanted to generate that model.
Sorry, can you ask again?
I say if I wanted to generate that model.
Yes, you want to generate it?
Yeah.
Okay, you need training data. Sorry, can I have 1 second? My mom
Of course.
like rushed into my room. I'm sorry.
Guess we can cut this out and edit.
Ja, ist gut, danke.
That's
Sorry.
That's all right. I'm sure we can cut this out in the edit.
Okay.
Yes, it's not a problem. It's rather a good example to give priority to mom. We can even post it on YouTube as a good example.
Fair point.
Okay, it's good. Sorry. Okay, you want to regenerate them. You will need training data, and the training data is located in NN prediction training train.py. Data here, CSV. Based on this training data, I normally use like 12 or so entries. So the time, then the full car state is the next 7. And then the next 2 is the control input. Oops. And the next 7 is the full next state. So I tried also to comment it in the training, but again, I don't know which method to save the training data is best. To generate it, I have this file, generate data. And my training data that worked for my models is just a random distribution of states. So I initialize it with 500 random initial states with uniformly distributed values. And for each of these initial state, I run a random normally distributed control sequence. And I just do then the steps with the car and save the history. Finally, I write it in this file here in the output file, which is just NN prediction training data and the file name. Yes, if you want to retrain it, you should run first this script. And I think I had good results with even small sets of training data, like 100 times 100 and like 10 as 10-point trajectory per initial state per command. Yes, and then you can just Python NN predictions training and train.py, and it will retrain the network with the constants that are defined here. Let's see. Yes, it works now. Now it's training, and it will save the network with this name here. Okay, I'm going to stop it because I don't want to overwrite my models. But in my experience, you have to reach an accuracy of about 95% of a large training data set to have good results for the controller. So it works with 94 maybe, but I think it's like the limit of a crashing controller.
And sorry, could you just throw up the training command on the screen again then?
Yes, sure. It's just I run the train script.
Thank you.
Okay. Good. I hope this explained it. What you asked.
It did, yes. Thank you.
Right.
So it sounds like the things that are of interest are the generate data command and the training stuff, and then the NN_predict folder seems to be like that's what we'll probably be doing most of the work.
Mm-hmm. Oh yes, sorry. The generate data command is also just Python NN prediction generate data, just like before, and it will. Yes.
Now that's doing the give it a random initial state and then roll out a bunch of okay.
And I think this is what you're going to replace, because we want to go away from this random initial states because it might be too difficult to collect it in the real world.
Yeah. What I was thinking might be a good way of generating data is to use your network with the MPPI control, but with like a variable number of rollouts, just to get like better and worse control. examples for the system?
Yes, yes, you could definitely try this. I tried actually with rounds around the track, but as soon as I had enough rollouts that the controller worked well, the trajectory was always the same. But your idea with different number of trajectories, this might work. It didn't work before because my controller was not so good when I tried this, and now it should work more solid. So yes, it would be nice to keep me updated if you have any success or questions or anything else I can help with.
Yeah, no, that would be. You will definitely be hearing from me.
Sorry, I
say you'll definitely be hearing from me.
Oh, okay, that's good. Yeah. Perfect.
Maybe two more questions on my side. First question: can you show where actually the CSV file is written? Because it is also probably a part which maybe needs to be changed. At least, yes, if Michel goes into the how you pronounce your name, Michael or Michel?
Michael, but Michael. I'm not too fast one way or the
other. So if you go, for example, for RNN, yes, now you have this different trajectories in one CSV file, one under each other, and then there is a risk that you will take the end of one like one trajectory and the beginning of the next, no, and you will have a jump. So you have to somehow deal with this problem, maybe saving it as separate CSV file or so. So that would be the first question. You are writing it here, okay?
Yes, I'm writing it here just row by row, and I don't make a difference between when I jump through the next state because I shuffle my data anyway, and I didn't do this at all.
And you have in one row always the current state and the next state, yes?
Yes, like I documented here. I have the time, then x1 to x7, u1, u2, and x1 next to x7 next, yes. If you do it sequentially, you could get rid of those because the next line would always be the solution to the current one. And I tried this, but I didn't have any success. But yes, so if you can generate data with a high variance on the test track, it might work, hopefully. Good.
One more question then from me. What does it need then to make it work in like full l2race? If we have now your car controller, how does it look like?
Okay, in the full l2race, let me get the right one. Desktop, this is it. Okay, this is the l2race. I showed you in the l2race opening presentation that there is a controller class that we can implement, like the car controller no, it's not car controller. Car controller.py, where we can implement those two functions, initialize and read just, this is the same like my run controller.py. So we have to give the car command back. And now l2race is implemented more beautiful than my state indices. So you actually have a car command dot steering and a car command dot acceleration. We have to change some things like this. But my neural MPC is here, neural MPC controller. I more or less literally copied the car controller class that I showed you before into the l2race project. This works more or less the same. And in the car controller.py implementation, I do this. I have the same commands like in the run mpc.py. So I get the next control sequence and I do like the first step of it, which is the MPC theory. And I return the steering and the throttle. And one thing I fought with was the unit conversion. It took a long time for me to realize that l2race actually works in degrees and not in radians. And I think the controller class does this. So this is a bit nasty, but as long as you only work on the predicting method, you can also deploy the predictor, and I will deploy it to l2race because I can just copy it to the working instance then. So you probably won't touch the controller at all. Okay, yes, the control step somewhere. Oh, the set state. This is why I have this set state function. In the although here I have to convert the units, and this function is more or less empty in the other project. Yes. Okay. So it might be quite easy to deploy a new predictor. Okay. Does that answer your question, Margie?
Yes, super interesting. Thanks. Follow-up question: what about this delta time when you are using it in l2race? And because now you train your neural network with some data where the next state is at fixed like time interval, and I guess it must match to some extent the time interval of l2race. How could you comment on it shortly?
I can, but I am a little bit ashamed for my solution. Okay. In the globals, I can define a number of trajectories, and this pretty one-to-one defines how fast the controller is. And I was trying until I got the number that matched how fast my controller was and how fast l2race was expecting the controller to work. And this might also be the reason that it didn't work in the Zoom presentation, because it's really fragile like this. It works if nothing else runs on my computer with those parameters. So if any one of you is interested in solving this problem, it's still unsolved, and it might be a simple solution, but I didn't have time to look at it deeper. I was so busy looking at my controller going through the racetrack that I forgot to make it more robust. Sorry. Yes. So you caught me here in a programmer sin. Sorry.
No, anyways, it's kind of working. At least it allows making super nice videos.
Okay, at least videos. Good.
That's it for this session.
Well, at least from my side it is.
I have also no more questions. Michael?
Yeah, no, I think I'm good. I think I know where to start poking around.
Okay, so thank you very much, Florian. It was really a great tutorial. You did a fantastic job as always. I will stop recording now.